All right, we're gonna go ahead and get going. I suspect more people might be on their way. It's a very important topic this week, but before I hop into the topic, just want to make sure that you're aware, of course, well, I'm sure you are aware that spring break is next week, so we won't be having class next week. But after spring break, a couple things to pay attention to. We have the exam coming up on the Thursday after break, so that'll be happening after you get back from break, and that means that the Tuesday after break, the next time that I see you in this room, will be an exam review session. So the Tuesday after break, I'll be running the exam review sessions in here for the second exam. This is the last new material that you're going to see before then. So 4, 5, and 6 are the topics that you're going to see on the exam, modules 4, 5, and 6. The other thing I wanted to mention is that late coupons. So if you want to use if you want to turn in assignment 5, which is due today, after break, you can do that. You can use your late coupons to do that. The clock's essentially paused while we're on break. Assignment 6 is not due until after break, so that shouldn't be a factor. Any questions about logistics coming up before I hop into recursion? Okay. So this is a very important topic, and I want to start out by just kind of making it clear that this topic relies very, very heavily on last week's topic. So if you are still struggling with methods, if you are not feeling confident with how methods work, if you're not, comfortable with that execution yet in the flow through the program as we follow along from one method to the next, I would actually really recommend that you probably spend some more time reinforcing those ideas. Because what we're going to talk about today is built directly on top of that. So if you do not understand methods yet, it's going to be very, very difficult to understand recursion. Methods are tricky, so I certainly understand if you're having some trouble with that. But the execution flow is particularly important. So the idea of calling methods and then returning once methods are over you cannot talk about recursion without those things, and so extremely important that you're aware of those concepts. The other thing that I would encourage you to be familiar with is, and to keep using, is the debugger. I'm going to be using the debugger on every example that we take a look at today. I think it's extremely useful for helping understand how these recursive methods execute, what it looks like as they execute. So I would encourage you to force yourself to do that as well, especially if you're confused or you just want to understand something a little bit better. But all that being said, let's jump into recursion. Actually, recursion as a concept is fairly straightforward. If I make a method here called hello, I can just have it print out a simple message like so, and then call itself. So this is a method call where the name of the method being called is the same as the method that I'm in. So the way to interpret this statement is that I'm going to print out this greeting, and then I'm going to saying go back up to the top and do it all over again. Print out the greeting, go back up to the top, do it all over again. I have to kick it off in my main method since that's where we always begin. So up here at the top I'll say, all right, this is where we begin, and then we'll jump down here and print out hello. This is not a particularly useful recursive program, but it is in fact recursive, and it will print out the message over and over and over and over again, repeatedly, until you can see that it actually crashes. To understand why that is the case and what exactly is happening here, let's see if we can find the place where it actually... So you can see that it does print out the message at first, and then eventually it crashes. So let's see if we can find that point where it stops printing out the message and starts crashing. Here it is. So what did it crash with? It crashed with something called a Stack Overflow error. So let's think about, let's try and understand what that means. This is a problem that's somewhat unique to recursion. To show you what I mean by a Stack Overflow error, I'm going to set a breakpoint here and start walking through this program. So here we are on the first line of the hello method that should print out that message. Over here on the left, I want to remind you that what we're looking at here is called the method call stack. So anytime I call a method, I see that method show up over here on the stack. So after I print out this message, it says call the hello method again. Go back to the hello method and start it over again from the beginning. So if I use the step into button to do that, you'll see that, all right, I'm now back up at the top of the hello method. And there's an additional entry for that hello method now on my method call stack. And I can keep doing this, right? I can keep stepping into those calls, and it'll keep adding those calls to the method call stack every single time. So you can see it's getting bigger and bigger and bigger. So this is an example of recursion, yes, but it's not useful recursion. So I want to show you a similar example that you've already seen, one that I did in class a little while ago that's very similar to the recursive example that I'm showing you. While true, right? Here's an example of a while loop that's just going to sit here and print out the word hello over and over and over and over again forever to infinity. That is also what this recursive method is doing. That's the claim that I'm making. It's going to sit here and print out the word hello, 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 hello forever. The only difference is that the while loop doesn't get interrupted by that stack overflow error. To understand why that happens, though, consider that this stack, this method call stack, is going to keep growing and growing and growing. And if it could, it would grow all the way until infinity. But that's not possible for something to grow to infinity. A computer is a finite object. And so at some point the computer just says, that's too much, right? I can't do it anymore. I can't fit any more method calls onto the stack. The stack is overflowing, right? Hence the overflow error. We've filled it up. You've called too many methods, we can't call anymore. So there's a limit. The limit's quite large. It's in the hundreds. You shouldn't really hit it in normal everyday use. It's usually an indication that there's some sort of a deeper problem going on. So let's address that. We didn't really like infinite while loops very much when we started talking about while loops. So we have a way that we can limit our while loops by, and one of the classic ways that we saw this is to introduce a counter, right? I equals 0, and then instead of having this true condition, what I usually want to see is something like this: I is less than 3. So the way that I solved a while loop, this infinite while loop, was to write a condition such that I expect that condition will eventually be false, and therefore the while loop will eventually end. In other words, I am, expect this condition to be true at first, but it will eventually be false. We can use that same idea with our recursive methods. In fact, we even have a name for this condition when it's used with the recursive method. It's called a base case. So the base case is a situation where we no longer perform recursion. I'm no longer going to make that call to the method over again. It's basically my stopping point. When do I want to stop? I mean, the stopping point for this example would probably look something like this. If I is less than 3, then I'm going to continue on. If it's not less than 3, then I'll just skip all that stuff and I won't do anything, right? I'm done. It's over. But you can see that the way that methods work, there's a little bit of a problem when I try to incorporate that loop variable I, right? The scoping rules of a method state that I can't see any variables inside of a method unless they're created within that method. Or another way of thinking about this is that every time that I take a trip through this method, right, the value of I needs to go up. So every time I make a pass through the method, the value of I needs to go up 1. That needs to be communicated from one method call to the next. And we have a way that we use to communicate from one method to the next called parameters. So in a while loop, I would just create a variable to use to track how many times I'm going through the loop. But since that's not something that I have accessible to me in a method, I will use a parameter instead. And what that means is that I now have to specify that parameter every time I call the method. So if I pass through this method and I want it to be, I want it to go up 1 the next time around, then I'll just say that here. I'll say the next time you go through this method, I want I to be 1 bigger than what it currently is. And when we go up to the very beginning, you'll see that, okay, for the while loop, I had to specify what the starting value was for my loop variable. Well, that's true for recursion as well, right? For the very first method call, I'm probably going to have that I value start out at 0, right? Although it's really up to me. I can pick whatever integer value I want here. But, you know, I'm making the claim that the code, this code here, is equivalent to, you know, the recursive method that I've got up here. In fact, you can very clearly see where all the parts appear, right? Very, very clearly see where the condition appears. The body is exactly the same, more or less, with the function call replacing that repetitive action. I want to go ahead and actually run the recursive method. I'm going to take this part out for, for just a moment and run this and show you that, okay, yes, it does in fact do what I'm trying to tell you that it does. It limits the recursion, right? I've instituted a base case. I'm now not going to recursively call that method forever. I've told it that there's a stopping point. There's a point in which I'm no longer interested in doing recursion. But let's walk this through the debugger. I think it's really important to kind of see, you know, exactly what's going on here, especially now that we've incorporated this parameter into the mix. So consider that the first time through the method, I starts out at 0. That's exactly what we said up here, right? I starts out at 0. So, okay, 0 is less than 3, so I'm going to go ahead and print out my message, and I'm going to tell it to run the hello method again. This time I want the value for I to be 1. If I step into this now, you'll see that, okay, I is in fact 1. But notice that the previous version of the hello method is still here. Didn't go anywhere. It's waiting. It's waiting for, you know, this one to finish doing whatever it's going to do. So let's follow it through. 1 is still less than 3, so I'm going to print out my message. And then next I'll call hello with 2 is the value. So there we go. You can see the stack has 3 copies now. I equals 2. Actually, if you click on these, you can see I equals 1, I equals 0. You can actually click on those and see the values of the parameters, the variables. All right, if I return back to the one that we're working on, 2 is still less than 3, so I go ahead and call hello. Now I is equal to 3. 3 is not less than 3, so now this time it actually skips. And because it's not calling the hello method again, the recursion is going to end. And all of these methods on the method stack, while Eclipse doesn't actually show that to you, I'll show it to you more clearly in the next example, will all end as well. And when I return back to the main method, we're now finished with the program. Are there any questions about that process, though? I think it's very important to understand that, you know, recursion is another tool that we have in our toolbox to perform repetition, just like loops. So really, there's nothing new, right? In a lot of ways, recursion's not giving us access to anything that we weren't able to do before. A lot of the things that you do with recursion can also be done with loops. I think you could probably even say that most or all of them could be done with loops, which might then make you wonder, well, why the heck are we even talking about this in the first place? I think that's a very valid question. If loops can be used for things, people generally like loops, find them to be a bit more intuitive when it comes to repetition. Why would we ever want to perform repetition this way? Well, the reason for that is that, you know, while loops are useful, and I myself use them all the time, there are some problems in which recursion is just going to be a better fit, a more natural fit than a loop will be. And I'll actually show you an example of one of those problems a little bit later on today. So while, yes, you can solve a lot of these problems using loops, in fact, all of these problems I think that we're talking about today you could solve using loops, there are certain problems in computer science where recursion is going to be a better fit, a better tool to solve the job than a loop would be. Any questions before I move on to the next example? All right, so the next example that I want to take a look at is from the textbook. It's actually going to be the factorial example. So I'm going to go down here and just rip it directly from the text. This is a classic recursive example, one of the very first recursive methods that people usually see. So just as a little refresher, right, about factorial and what it's doing, if I tell you I want the factorial of 3, that means that I want 3 times 2 times 1. If I tell you I want the factorial of 6, that's 6 times 5 times 4 times 3 times 2 times 1, right? Or I would actually encourage you to write it out. Get out a sheet of paper, or I'm going to do it on the computer. If I could say something like the factorial of 3 is equal to 3 times 2 times 1. I want to make the claim, though, that I could rewrite this slightly differently if I wanted to. If I look at this right here, I want to make the claim now that that's actually the factorial of 2, correct? So if I wanted to, I could rewrite the factorial of 3 as 3 times the factorial of 2. Does everybody follow with me so far? Okay, and I could do something similar with the factorial of 2, correct? The factorial of 2 is going to be equal to 2 times the factorial of 1. And the factorial of 1, we could apply the same rule. It's equal to 1 times the factorial of 0, right? You can see the pattern here. But when do we stop? When do we stop? Well, for a lot of these that mimic mathematical equations, we're typically going to stop whenever we hit a known value. So the known value for factorial in this case, the factorial of 0 is given as 1. It's just defined that way. By definition, the factorial of 0 is 1. That's how it's defined. A lot of times when you see those values given to you by definition, that's a very natural base case. So if I work my way all the way down to 0, I can just say, all right, the factorial of 0 is 0. And if you come down here and look at the code, you can see that's kind of what it's trying to do, although computer code really wants to be more general. So while, yes, this is how I would compute the factorial of 3, when I'm writing the factorial method, I need to think of it in more general terms, or in computer science we'd say that we need to abstract it. In other words, I want to figure out really what's the definition for the factorial of n. And the way that I wrote this out, hopefully you can see what the pattern is for the factorial of n. The factorial of 3 is 3, which is n, times the factorial of 2, which is n minus 1. The factorial of 2 is 2, which is n, times factorial of 1, which is n minus 1. So if I'm writing this out in terms of factorial of n, it's going to be equal to n times the factorial of n minus 1. That does in fact apply to all of these lines, right? The base case then, when n is equal to 0, is given as 0. And with those two pieces of information, here's my recursive call, the method that I'm writing, defined in terms of itself. And here's my base case, when I'm going to stop. So those can very easily be translated into code when n is equal to 0. Whoops, that's my mistake. It's not 0, it's 1. It should be 1, my fault. Otherwise, I'm going to return n times the factorial of n minus 1. Does everybody understand how I got there, though? I mean, I think that's really the more important piece to take away here. If you looked at this code and you understand how it works, that's fantastic. But I'm going to ask you to think of a problem and turn it into recursive code. And so what I need you to do is, be able to think about how to solve a problem like this and come up with solutions that look like this so that you can then turn them into code. That's the tricky part. It's not easy. Let's work through this factorial example, though, and really make sure that we understand how this factorial example works. Because unlike the prior example that we saw, this factorial example is returning something, right? When I say, give me the factorial of 5, it's giving me back the answer. It's not just printing it on the screen. It's saying, here you go. Here's the number that you asked for, that you wanted me to compute. So let's see how that affects our execution. I'm going to do what I've been doing, which is to set a breakpoint here and run this through in the debugger. Okay, so here I am at the very first step. I want to call the factorial of 3, which should just be 3 times 2 times 1. Okay, I'll step into this. 3 is not equal to 0. This is my base case, so I'm going to skip it. And now it says return 3 times the factorial of 2. Well, notice where I'm going to go next. I'm actually not going to do any multiplication right now. I have to go figure out what the factorial of 2 is first before I can perform that multiplication. So let's go figure out what the factorial of 2 is. If I step into this method, you can see that now n is equal to 2, which is still not 0. So I'm going to jump down here and say, all right, give me 2 times the factorial of 1. So I'm still not going to do any multiplication. I have to go figure out what the factorial of 1 is first. Oops, that's not the right button. There we go, that's the right button. 1 is still not 0. And be sure to notice the call stack over here too, right? All those recursive calls are waiting, sitting around waiting. Still not 0, so 1 times the factorial of 0. Okay, here we go. N is now equal to 0. I've hit my base case. Did you have a question? The code's not running backwards necessarily. I mean, I think I understand where your question's coming from. The code's doing exactly what I told it to do. There's no backwards. The code runs the same way every single time, exactly as it's written. The computations that are being performed, though, are not actually going to happen until I go back up, which I'm about to show you here in just a second. What I mean by that. I want you to remember that all of these other methods for n equals 1, 2, and 3, they're not done. They have not figured out their answers yet. They are sitting around waiting for more information before they can figure that stuff out. So here I am at my base case, n is 0. I know the answer for 0. It's defined. Right? It's defined for me. The answer for 0 is 1. So I'm going to return that information. Remember that when a method returns, that means that it's over. That means that the method is now over. I know what my answer is. My answer is 1. I'm going to take that answer of 1 and I'm going to pass it up the call stack to here, to the previous method, right? So I know that this value is 1. N is 1. That's always been the case for this particular method. So now I can do the multiplication. 1 times 1 gives me 1. Well, that was pretty easy. I'm going to take that value and return that up to the prior method call for when n is equal to 2. So if I do that, you can see, all right, the value for n is equal to 1 is 1. 1 times 2 gives me 2. So I'm going to take that value of 2, return that up to the method call for n is equal to 3. And now I can compute for n is equal to 3, 3 times 2, which gives me the value of 6. And if I go back, or if I hit step now, you can see there's my 6 right there. That is the final result of factorial of 3 that we've asked to be computed. In fact, I'd say that this example that I drew out here, if we wanted to, we could even incorporate kind of what you were talking about, right? Take notice that, okay, now that I know what the factorial of 0 is, what I was really doing is saying take this value and substitute it in here, right? So now what I actually want to do is say the factorial of 1 is equal to 1 times 1, which is 1. And now that I know that the factorial of 1 is equal to 1, I can take that value and I can substitute it in here. And I can recompute that. Okay, so the factorial of 2 becomes 2 times 1. And now that I know what the factorial of 2 is, I can substitute that in here. Oops. So this little pattern that I've sketched out here is how all recursive methods are going to execute. They'll keep doing recursive calls all the way down till they hit the base case, but they have to go back up Just because we've hit the base case does not necessarily mean that we're done. There might be more work that has to be done as we traverse back through all of the methods on the way back up the call stack. There may not be. Our very first example was an example of when there wasn't. The work was being done only on the way down, not on the way back up. It can be both. I can do work on the way down and on the way back up. Right? There's nothing stopping me from coming down here to, do some work here, and then do this method call, and then maybe, do some more work after it, and then return something. Right? That's all possible as well. There's no limits on what code I can put here, in other words. Right? So while the recursive examples that I'm showing you today are fairly simple, fairly straightforward, they tend not to do a whole lot of computations at one point in time. In real life, there's no limit to that. You have to make the code match whatever problem it is that you're trying to solve. So we do this enough times that we actually have a name for it. In fact, I'm going to ask you to do something like this on the homework assignment. And I'm also going to ask you to do something like this on the next exam. If I ever ask you to perform something called the substitution method, this is what I'm referring to. This is the substitution method. Go down to the base case and then substitute the values back in on the way back up to compute your answer. That's the substitution method. I'm not picky about the format. You don't have to write it out exactly like I've written it out here. But I do want to see all the method calls. I do want to see you hit the base case. And if there's computations to be formed on the way back up, then I want to see those computations. So however you can express that to me doesn't really matter. I think this way is pretty clear and straightforward. Question? Sure did. Yeah, in fact, if it'll help, I can run through this again and show you, all right, factorial of 3, that's where we're at right now, right? The very first part of my substitution method. So if I step into this again, I'm not in my base case yet. So factorial of 3 is equal to, n is equal to 3, right? 3 times the factorial of 2. That's exactly what I said here. Exactly what I said there. So here I am at the top. If I step into this, I go to the next one, n is equal to 2, and it's going to tell me the same story. Factorial of 2 is equal to 2 times factorial, exactly what I wrote down. So I'll keep doing that until I get to the, oops, did I do it wrong? Until I get to the base case. I did it wrong, I'm sorry. Let me get to the base case. When n is equal to 0. So here I am at that point in time. I'm now here. Factorial of 0 is equal to 1. N is 0. I give you back 1. So now I'm working my way back up, and I'm doing the substitutions. I now know what the factorial of 0 is, so I'm going to substitute that in here. And as I step through, right, the factorial of 0 is what I just computed. That's 1. 1 times n, which is 1, is 1. And I'll keep substituting that. So that's this line. And I'll keep substituting that in all the way back up until I return to my original method call, factorial of 3, and I finally got my answer. It's not until I get here that I actually know what the answer is. Question?
Once you get the base case, then the code is not likely to get selected.
Absolutely. Yes, that's correct. There's again, I want to reiterate that when I hit a method call, I am inside of the factorial method. I still have more work to do. It's saying compute n times the factorial of n minus 1. I cannot do that until I figure out what this is first. So I'm going to go figure out what that is first, and then I'm going to come back and do the multiplication once I know what that number is, once I can substitute that value in. It's not physically possible for me to do the multiplication before that. I don't know what that is. Does that make sense? I hope. I don't know what the factorial of 1 is, so I have to go figure it out. And then once I know what it is, I'll substitute it in, compute that value, and keep going. So the next example that they ask you to work through is very similar to this one, actually. They give you an example called, I'm going to work through both of these coding practice problems with the time that I've got left. They ask you to open up the sum program. So this is a very, very similar problem to the one that we just looked at, but not an uncommon way to be presented a recursive task. And so I hope that if you are presented a problem like this, that you can see, here's the recursive step. I see that the sum of n is defined in terms of itself, right? And then here for this other part down at the bottom, there is no recursive call here. This must be my base case. Excuse me. Those are the two parts that are going to be in every recursive method that we ask you to write. We're never going to ask you to write a method that's infinitely recursive, not without at least giving you a big heads up first. I don't think that would ever happen, though, actually. So, here's my recursive step. Here's my base case. But furthermore, I would encourage you to work through an example, work through the substitution method. That's what I like to do with this problem. Just keep reinforcing the idea of substitution method. So if we start with the sum of 4, for example, just following along the logic given to us, that's going to be the sum of 3 plus 4. So we'll just write that out accordingly. And then the sum of 3 is going to be equal to the sum of 2 plus 3. Sum of 2 is going to be equal to the sum of 1 plus 2, 0. And then I think we are now at our base case. Let me check here. Yeah, so if n is, our base case is if n is less than or equal to 0. That's the opposite of how it's phrased here. I mean, yeah. Then I know the answer is going to be 0. That's our known value. That's our defined value. And now we can start substituting back in. Sum of 1 is going to be equal to 0 plus 1. I believe this is actually, just like the factorial problem, except with addition instead of multiplication. But it's still a good idea to reinforce the execution through these recursive methods. So here's what the substitution method might look like, for this recursive method. Notice that I have worked this out without even writing any code first, right? I think that's useful to be able to do. If you can do this, then hopefully turning this into code should be fairly straightforward. You can clearly see the base case right here in the middle is when the value is 0. And then for each of these, we just need to figure out how to generalize it, i.e. write it in terms of n. So if you can identify the pattern, right? The sum of n is equal to the sum of n minus 1 plus n. Okay. If n is greater than 0, return sum of n minus 1 plus n. Else return 0. I believe that's it. I believe this is the way to take that and turn it into code. We, of course, are going to be asking you to do this on the studio and in the homework assignment that's coming up. Question? My argument would be that it doesn't matter. If I wanted to, I could simply flip the sign here. Say if n is less than or equal to 0, then the only effect that that's going to have is just flipping the order of these two, right? So it's the same thing. Any other questions on this example? So all of the examples that I've shown you today are sort of math-based so far, with the possible exception of the first one that didn't really do any math at all. And you're going to see more mathematical problems in the studio and the homework assignment. That's a very common situation that we ask you to apply recursion to. There are a lot of recursive formulas that you're going to run into. Maybe you've already seen some examples in your calculus classes or your stats classes, stuff like that. But there are other categories of recursive problems as well. And one category that I think works really well with recursion are geometric problems, or problems in which I'm drawing certain patterns or shapes of shapes and things on the screen. So we've seen how to use the computer to do stuff like that. You've worked with standard draw for a few weeks now. You're familiar with how to draw shapes and things like that. And so with the last example, the last recursive example I want to show you today is how to draw some graph paper recursively. I think this is a great example of, when I would probably choose recursion over loops. I think for almost all of the examples I've shown you today, if I really wanted to do any of the examples, the factorial or the sum example, I'd probably use loops to do those, right? And that's okay if you would as well. We're showing them to you to help you understand how recursion works. Now we've kind of got a little taste of recursion. Let's consider that a sheet of graph paper is just, paper with a grid drawn on it, grid of squares. So where does the recursion lie? If we think of it as, all right, I'm going to take this very, very big sheet of paper, I can turn that into a sheet of graph paper very simply by bisecting it horizontally and vertically, right? It's now a big sheet of graph paper. It's got a grid on it. That's all it takes, is 2 lines to make it into a grid. But okay, what size graph paper do we want, right? I probably want to have, small squares for my graph paper. So once I've drawn a horizontal line and a vertical line bisecting my space, we can recognize the fact, well, I could actually take each of the 4 quadrants that is left, right, and turn those into graph paper. So in other words, each of those 4 quadrants is essentially a smaller sheet of graph paper. And I can construct a big piece of graph paper by making lots of these little tiny pieces of graph paper and sticking them all together. That's a recursive approach to this problem. Let's see if we can work it out. So we've given you some help here to get things set up for you. You've got a recursive method already supplied where you're given 2 coordinates, an x coordinate and a y coordinate that represent the xy position of the lower left corner of the square that we're currently working with. Okay? So our first task then is to draw the lines that need to go across that square. One going horizontally all the way from left to right, and one going vertically all the way from top to bottom. We know how big the square is as well. That's what this third parameter is. We've even provided you with the base case. I'm going to come back and play with this base case a little bit later on because I think it's kind of fun. But our base case in this situation is based on the size, and that's actually going to be true for most geometric, for most visual problems. The base case is going to be based on the size. Essentially, after things get too small, we can't even see them anymore, right? So we might as well stop. That is a very common base case for these visual types of recursive problems. Just stop when things get too small. But now it's our task. We need to draw the lines. So I need to draw a line that goes across from left to right, splitting it in half, and one that goes from top to bottom, splitting it in half. This is the easy part. It does require a little bit of thought. I actually pulled up Paint last time and sketched out a square and did a little bit of, I might even still have it. But if I'm thinking about, all we have is the xy coordinate of the lower left corner. Here, let me pull up the diagram. Yeah. This is my beautiful diagram. This is the only information that we have available to us, this point. But I need to draw this line. So in order to draw this line, I need to figure out what this point is here and what this point is over here. So for the horizontal line, the y value isn't going to change, right? The x value is the only one that's going to change. So, okay, our x value will start out as the lower left x. The y value is halfway up, so it's our y value plus half of the size. Then the second x value will just be all the way on the other side of the square. So if we start here, our corresponding x value is all the way on the other side. So I just have to add the size. And then the y value actually doesn't change. It's the same, right? So I can just borrow that again. And at this point, I'm actually going to test it. It's not recursive yet. It's not going to draw a graph paper yet. I just want to make sure I got this line correct. All right, there we go. One horizontal line moving directly across. That's good. Now I need to do my vertical line. So similar story. This time the x value needs to be in the middle. So x plus size over 2. The y value is going to go from the bottom to the top. Okay. I think that'll do it. Let's run it and see if this is going to draw the cross. There we go. So let me pause here, make sure you all understand what I've done and then also what I'm about to do. There's no recursion happening here yet. I have told it to start with the lower left corner of 0, 0, right? That's the very bottom left corner. The square size of 1. That's the entire canvas. So it has used that information, those coordinates and the size, to draw a line going across horizontally and a line going across vertically. The next step that I'm going to take is to say, all right, now move to the upper left corner and draw the lines there going across horizontally and vertically. And then do the same for the upper right, the bottom left, and the bottom right. Question?
So just to clarify, are you drawing like for example, the horizontal line, are you drawing like almost like one point where it was going up and
That's how the line method works, yes. Draws a line segment between x0, y0, and x1, y1. Yeah, from the standard draw API. Sorry if I went through that too fast. That's from a few weeks ago. So there's going to be actually not just one recursive call here, but 4. One for each of the 4 quadrants. So I'm actually going to start with the lower left quadrant first, right? And so think about it. What I want to do is my recursive call, and every time I call this method, I have to supply these 3 values. So I have to now figure, okay, I'm given the lower left xy coordinate for this big square and the size for this big square. I now need to figure out what the lower left x and y coordinate is for this square here and what the size is going to be for this square here. Well, this is the simplest one. That's why I started with it. The lower left and x and y coordinates don't change. They're exactly the same, right? Because I'm in the lower left quadrant. So this is the easiest one to do. The size does change. The size of this square is half as big, I would say, right? Or the length of the sides is half as big as the one that we started with. So I'll reflect that by saying size over 2. And this is now recursive, right? It's not going to be complete. We still have some more work to do, but I want to run this and show you what's going to happen. There's the big square, and you can see it's going down and to the left, down and to the left, down and to the left, and it keeps drawing those crosses as it goes. And each time the square that it's looking at is half as big, right? Because I'm dividing the size by half every time I call that method. Shrinking down, shrinking down, shrinking down. Okay, let's take a crack at the lower right corner next. So I'm going to copy this and try and I'll make a note here so I remember which one it is. Lower left. I'm going to try the lower right. So if I'm thinking about this, I have this coordinate and I want this coordinate. So the y coordinate is not changed, right? It's still the same. The x coordinate has, though. It's shifted over by size over 2. The y coordinate remains unchanged, and the size of the square is still halving as well. So I think that's it. Let me close these out and see what happens now with the lower right quadrant included. There we see it going down to the left, and once it gets all the way, whoops, I've got a mistake. It would appear that's not right. Where's my mistake? Here it is. And I found it so quickly because I made this mistake before last time. I get sloppy with my copying and pasting, right? It's supposed to go x, y, x, y. And if you look, I have y's for all of these. I don't have any x's. So that's me being sloppy with the copy pasting, right? That's my bad. All right, let's try that again now that I've fixed the mistake that I made. Hopefully we'll see those crosses get drawn. There we go, that looks good. And then once it gets all the way as far down as it can go in the lower left, you'll notice that it starts picking up the lower right. That's kind of cool. All right, 2 more quadrants to go. So now I'll do the upper left. So now the x coordinate's going, I'm sorry, the x coordinate's staying the same, and the y coordinate is going up by size over 2. So we can see what this one would look like. And we'll add the last one on there in just a second. You can already see that it's working, right? Because I see the 3 quadrants for each of the smaller squares getting filled in too. That's kind of cool. All right, I'm actually going to speed this up. There's a half-second pause that's been inserted. I'm going to make that a little faster for this last one. Upper left, and then, whoops. There we go. Chugging along a little faster now, and you can see it's actually filling in all 4 of the quadrants. If we let this go on, it'll eventually fill up the entire grid space. You can, of course, keep messing with the pause time to make it go as fast or as slow as makes you happy. You can mess with the colors and such as well. But one thing that I kind of want to mess with, to show you the effects, is the base case. So if I come up here to the base case and I make it even smaller, right? That means that it's going to try to make even smaller squares before it stops. So just by changing the base case here, we now can actually manipulate how we want our graph paper to look. And I don't know, I may have gone too far down that time. Those squares are pretty dang small. You can't even, I can kind of see them if I get like, yeah. But probably want to pick something a little bit bigger, perhaps. So, I would encourage you to fill around. That's not too bad if I'm looking for, small squared graph paper. So I would encourage you to fiddle around with this on your own, right? See what the effects are of changing each of these values on the overall result. Again, I want to reiterate that this is actually pausing on purpose. It doesn't actually take that long. If you take the pause out or mostly take it out, it'll go fairly quickly, right? And crank this out pretty fast. So it's arbitrarily slowed down so you can see the recursive pattern. But in practice, if done properly, you don't necessarily see the difference between recursion or using a loop to solve a problem because they both get you to the same place, right? And so the last thing that I want to say about this problem and recursion in general, the fact that I have 4 recursive calls here, right? 4 recursive calls here. Very common when dealing with these geometric kinds of patterns. This is a great example of when I would prefer to use recursion. Could I have used loops to make this graph paper? Absolutely you could. You could even go home and try it if you want to. You know enough to do that if you really want to. But I think that this very naturally fits recursive style. In fact, we have a name for this category of problem. Anytime you see this type of problem where you start with a big space and you subdivide it into smaller spaces, we call those divide and conquer problems. So I take my big square, I turn it into 4 smaller squares where I have one recursive call for each of those quadrants. That's my dividing and conquering. Classic category of problem that is used with recursion. If you proceed along into 247, which is the data structures class that a lot of people take after this one, you'll learn a lot more about that category of problems, and you'll be expected to use recursion to solve those problems regularly. That's how it's done. So while a lot of the examples that I illustrated maybe aren't practical uses for recursion, this one I think is. A lot of the divide and conquer problems are. And even if you aren't going to compute sums or factorials using recursion in real life, still good examples to show how recursion works. Okay. That's it. That's all that I have for you. I just wanted to show you some simple examples. You're going to learn some more stuff about recursion in Studio on Thursday, and I'll be there as well. I'm happy to stick around and answer any questions that you have. If anybody wants me to go through any of the other examples from the textbook, or even go through some of these examples over again, I would be more than happy to do so. If you want to come up and ask me questions about homework or other stuff, I'll be here. I'm around. Let me know how I can help you or what I can do for you. Otherwise, I hope you have a good rest of your week, and I will see you in Studio on Thursday.